All right, so today's January 6th, guys, but reminder, okay, your climatograms activity is due January 8th, all right? So that's Wednesday, that's coming right up. If you still need to talk to your group members about that, okay, make sure that you see them. I also posted climatograms for all the cities that are on your activity on my website before Christmas. So if you can't meet up with your group or you didn't have a group or whatever, you can look at those ones. They are not all to the same scale. Okay, unfortunately I just couldn't find them all to the same scale, so they're the best I could find. You can use them and you'll be able to get it done with those. All right, so make sure you have that. Guys, I would imagine our unit exam for this unit will be next Wednesday. All right, so expect that that is probably when that will happen. If we're done early, great. All right, we'll review for the exam. We'll start looking at final exam stuff, but our unit exam will most likely be next Wednesday. All right, and then we will have Thursday and Friday to do final exam prep, and then you're done. So yeah, I hope you hit the ground running today, because if you didn't, you're going to roll along in a little pile into the ditch, okay? Because it's got to go fast here for the next 2 weeks. All right, and it's going to be that way in all of your classes, so I hope you rested up, okay, because you're going to need it now. All right, so today's lesson, okay, is lesson 3, and we're going to be looking at energy transfers, okay, within the Earth's system, okay. So we're going to look at essentially the 3 methods of heat transfer, okay, the 3 ways that heat gets transferred and how those kind of happen, all right, within the Earth's atmosphere, within the Earth's crust, within the Earth's oceans, how those 3 parts of the Earth interact, okay, things like that. Okay, so we got to look at those 3 parts of the Earth. We'll learn their proper names, okay, understand how energy on Earth is absorbed, used, and reflected, okay. Those are essentially, guys, the 3 things that can happen to solar energy when it strikes the Earth's surface. Okay, it can be absorbed. If it is absorbed, what will happen to the temperature of that area? It will increase. Okay, so anytime you have solar energy being absorbed, okay, you will have a temperature slash energy increase. Okay, if it is reflected, okay, will the temperature change? No. All right, there'll be no change in energy, no change in temperature, because the energy is simply bouncing off. All right, what kind of surfaces on Earth do you suppose that happens most with? What surfaces on Earth reflect solar energy the most? Water actually absorbs quite a bit, especially if it's deep ocean, because water is clear, right? And so the rays can go through into sort of the darker areas of the water where they will be absorbed. Okay, some of it does. It depends on the angle it comes in at, but most of the time, if it's directly overhead, it absorbs quite a bit. Depends. If it's a hot desert where it's mostly sand, the answer is no. Ever walked on a beach in the afternoon? Right? Like if you go to a tropical place and you try and walk on the sand in the afternoon, it's hot on the feet. Okay? There was this back way probably before you were born. There was this commercial, Pepsi commercial, where people were like, they would do this little dance along on the hot beach trying to get to the Pepsi stand. It was a stupid ad, but anyway. Okay? Yeah. So deserts tend to be rocky, sandy, things that absorb a lot of solar energy, so they get hot. They absorb a lot. Snow. Okay? Snow is a high reflector. Because it's what color? White. Okay? Anything that's white is reflecting essentially all wavelengths of light back off. All right? And so that's what we're looking for there, is anything that's light in color, closest to white, reflects a lot of energy. So wintertime right now for us is a really low energy situation. We already talked about how the solar energy is at a bad angle. It's coming in at a, we're tilted away, so it's coming in at a bad angle. We're tilted away, so we only get 7 hours of it. And the ground's covered in snow, which reflects the majority of it away, right? We just don't have any chance to really get any energy changes going, all right? The other one is used, okay? And sometimes we use the word converted, okay? What naturally occurring things would convert solar energy into something else? Plants convert it into chemical energy with photosynthesis. That's the only thing. Okay? The only things capable of directly converting solar energy into something else that are natural, okay, are plants. Right? And so if it is being used, it is being converted, and it is being converted by this process. Okay? That right there, guys, is the basis for all life on Earth. Without the producers, there would be no food for anything else. Okay, so without plants, which thankfully are plentiful, okay, there wouldn't be any conversion of solar energy into useful forms. Okay. And then lastly, understand how the energy on the Earth, the energy and the Earth, sorry, interact to produce the conditions necessary to support life. All right. So first part of the Earth we're going to look at is the one that has the most to do with transferring energy from place to place on Earth. Most of the transfers of energy occur within the atmosphere. Right? Why would that be? Why would the atmosphere be the best part of the Earth for transferring energy from one place to another? Partially, it is the first place that the solar energy encounters, okay, but it's rather thin, and so energy goes right through it pretty easily, but it does absorb some. Is there any part of the Earth that really isn't, any part of the surface of the Earth that isn't in contact with the atmosphere? Nope. Okay, so it touches every place on Earth. All right, so that makes it a good way to transfer energy from one place to another. It can transfer it to anywhere because it's everywhere. All right, and the third reason is it's the most fluid. Okay? Air moves more easily than any other part of the Earth. All right? Can the ocean move? Yeah, I mean, there's currents within the ocean, but the ocean doesn't just decide to walk up on the land and take over new territory. Well, it sort of does, but very slowly. Okay? So it's not really, it can transfer energy. It certainly has a huge part to play, but not as much as the atmosphere because it isn't as fluid and it isn't in contact with every place on Earth. We ought to know that where we are. Okay? Right in the middle of a continent. Yeah, we don't get a lot of that benefit that we talked about before Christmas of the ocean regulating temperature. We're too far away. All right. What about the solid part of the Earth? Does it play much of a role in transferring energy from place to place? Not too much. Okay. I mean, rocks generally don't transfer heat very well. All right, and that's generally what the Earth is made out of. So it's doesn't have a really big part to play. The part it has to play is absorption. It's usually the darkest part of the Earth, okay? And so it absorbs the most energy. And if it's absorbing energy, the air above it can do what? If the ground below gets hot, what does the air above get? Hot. Okay? They transfer, right? It always flows from hot to cold. So if the air above is cooler than the ground below, the energy flows from hot to cold. Right? And so it helps to warm up the atmosphere. All right. You're not going to need to know the layers of the atmosphere. I'm never going to have a multiple choice question or a written response question that asks you about the names of the parts of the atmosphere. They're mostly trivia. Okay? I just have them on there because it helps to explain a couple of things. Okay, so it's layers of gases that surround the Earth. Okay, the most important layer for us, the layer where most of our weather occurs, where the important gases for our survival are, is the troposphere. Okay, the troposphere is the layer closest to the Earth, goes up about 16 kilometers. Okay, so 16,000 meters roughly. All right, which basically includes all the parts of the Earth you could stand on. All right, including Mount Everest, although Mount Everest is pretty close. Okay, to the stratosphere. All right, you don't want to be up there for too long. All right, so stratosphere extends from roughly 11 kilometers to 50 kilometers. The stratosphere is where things like the jet stream occur, okay, and things like that we'll talk about later on in the unit. Okay, and then above that are the mesosphere, thermosphere, and exosphere. Okay, thermosphere and exosphere have mostly to do with our magnetic field and stuff like that. There's not enough air there for anything to survive. Okay, these are really only a concern if you are a let's say a Soyuz capsule pilot, right, or a space shuttle pilot or something, and you're re-entering the Earth's atmosphere. That's where you'd start to get really hot. All right, so that would really only be a concern for them. Oh yeah, the Stratus guy. I can't remember what his name was. Yeah, Felix Baumgartner, right? Yeah, yeah. He was into the stratosphere for sure. Okay, possibly above that. Yeah, it was a big jump. All right. So big thing with the atmosphere here, guys, is that it contains those gases and creates the pressure that we require in order to survive. Okay. It's the fact that there's all these gases and that they're being pulled towards the Earth by what? By gravity. Gravity creates atmospheric pressure. All right? Without the Earth's gravity pulling the atmosphere down on top of us, okay, we wouldn't be able to survive. The Earth's atmospheric pressure keeps the gases that are normally in our blood dissolved. All right? Without that atmospheric pressure, what happens to them? They turn into bubbles. Okay? They start to boil. All right? If you take, if you leave a pot of water out on the Earth's surface, it just sits there. It's good. Okay? If you did that with a pot of water on the surface of Mars where there is 1/100th of the atmospheric pressure, it would boil away, even though it would be well below freezing. Okay? It's a funky thing to see. Okay? But if you have a pot of water in a room where you can pull the air out, okay, it starts to boil, even though you haven't added any heat to it. At room temperature, it'll just start to boil, okay, because there isn't enough pressure to keep it in a liquid state, and so it turns into a gas really quickly. Okay? In fact, that happens the higher up in altitude you go. In fact, here in Okotoks, where we're about 1,100 meters above sea level, water boils at less than 100 degrees Celsius. It's around 96. Okay? If you're climbing Mount Everest and you're making Ichiban, which is what a lot of them make because it's lightweight and easy to carry, okay, water boils at about 65 or 70 degrees. Okay? You got to eat that stuff fast or it'll be cold. Okay? Because you can't, once it starts to boil, it won't get any hotter than that. Okay? It turns into a gas. So your Ichiban is going to be 65 degrees. You better eat it while it boils. Okay? Because if you pull it off the burner, it'll be frozen noodles real fast. Okay, so pressure is important. It keeps gases and other things in the state they're supposed to be in. Okay, if we get too far out of that pressure area, then the gases within our blood will start to bubble. Now, you might think, well, that's not such a big deal, but it is, because your blood vessels will get blocked by these bubbles. Okay, and that can cause things like strokes and aneurysms and things like that. Okay, if those bubbles expand, it becomes very painful because they exert a lot of pressure against the inside of your blood vessels, your muscles. Okay, imagine the worst muscle cramp you ever had. Okay, everyone's had like that cramp in your foot, the one you can't get rid of. Right, doesn't matter how you move your foot, you just lay there and writhe because you can't get rid of that one. Okay, imagine that, but like exponentially worse, and all over your entire body. That's what it's like when you start to get the bends. Okay, and the bends are caused by these gases bubbling out. Okay, now if it gets really bad, it'll break the blood vessels. Okay, and then you have a brain bleed, especially if it happens in your brain, capillaries in your eyes. Yeah. Okay, it's nasty. All right. Yeah, you don't want to go that way. Okay, it would not be a pleasant way to go. That's why you put on a spacesuit when you leave the International Space Station. If you're going out the airlock like those guys did over Christmas, they tried to put all those cameras on so you could have streaming live video from the space station. It didn't work. But okay, they were out there in their spacesuits for hours and hours trying to get that to work. You have to wear a spacesuit in space. If you don't, you'll boil. Okay, and pop, and it would be unpleasant. Yeah, you wouldn't like itchy and scratchy pop, okay, but you would rupture, okay, and the first place is the weakest place. Okay, your eyes would go first. Yeah. Okay, it would be bad. What's that? Yes, yeah, your tongue would swell, you wouldn't be able to breathe, everything would just, it'd be nasty. Okay, so the atmosphere, kind of important. Okay, kind of important. Atmospheric pressure, very, very important. Okay, and that's the same reason why, guys, on a plane, okay, if you were to lose, like if someone were to rupture the skin of the plane while you were at a high altitude, what happens to all the air? It rushes out because there's so much more pressure inside the plane than outside the plane because you're very high up. You're in the stratosphere usually, okay, when you are flying in a plane, and so as a result, there's way less pressure outside. All right, and so you don't get sucked out, you get blown out. All right, same with an airlock. Have you ever seen that when they open up an airlock in a science fiction movie? Everything kind of just goes flying out. It's not getting sucked out. It's getting blown out. There's no pressure out there. There's pressure inside, and it all just quickly tries to equalize. Okay, yeah. All right. So, the atmosphere and climate. Some important things here that the atmosphere does. Okay, plays a critical role in maintaining the Earth's temperature. Okay, without the Earth's atmosphere holds a lot of heat in. All right, we call that the greenhouse effect. It's a good thing. I know you've never probably been told that before, but without the greenhouse effect, the Earth would be a frigid ball of ice. All right, we need the greenhouse effect in order to keep heat in and to maintain a proper temperature. Now, is the greenhouse effect getting worse? Yes. Is that a good thing? Probably not. Okay, but without the greenhouse effect, we'd be in real trouble. All right, you look at a place, like Venus. Obviously, that's kind of out of control. All right, we don't want to have a greenhouse effect like that because we don't want battery acid rain and 3,000 degree temperature. Okay, not 3,000. It's about 800 and something. Okay, it's really hot. Melts lead on the surface. Conversely, if you look at Mars, with 1/100th of the atmosphere we have, it has no greenhouse effect, and all of the heat just bleeds away into space, and it can be minus 100 and something. Okay, at various points on the surface. So, okay, the atmosphere is important in regulating and maintaining temperature. Okay, it's also important in that parts of the atmosphere protect us from the sun. Okay, what part in particular? The ozone layer. Okay, the ozone layer blocks ultraviolet radiation. Most of the other rays also get blocked, okay, by the Earth's atmosphere, okay, and the magnetic field of the Earth as well, keeping things like gamma rays and X-rays and things that are really nasty from reaching the surface of the Earth. Okay, and so if there's spots where the ozone layer is thin, and there are, more UV light gets in. Okay, luckily the X-rays and gamma rays are blocked whether the ozone layer is there or not. No, the moon does not have enough gravity to hold it, to hold the gases in place. You would have to add mass. I don't know where you get that from. I suppose theoretically if you pounded it with a bunch of asteroids and made it heavier, but that would have other repercussions for us. If the moon was heavier, it would pull on us harder, and the oceans would reach out onto land and swallow up lots of things as the tides came in and out all the time. Yeah. Okay. We got this incoming solar radiation reflected away, okay, from the Earth by those particles. Water vapor and ozone are especially important. Okay. On the Earth's surface, we're looking at something called albedo. Okay. Albedo is the reflectivity of the Earth's surface. Right? We already said the most reflective thing on the Earth's surface is snow. Okay? Snow has a very high albedo. Right? The higher the albedo, the more reflective the surface is. The lower the albedo, the more absorptive the surface is. So if you were in Hawaii and you're on the volcano and there's nothing but that black basaltic volcanic rock, that is a very low albedo. All right, it absorbs practically everything that comes in. All right, so darker colors tend to have a lower albedo and absorb more solar energy than lighter colors. Okay, and you probably experience this if you have like a dark colored interior in your car. Right, in the summertime you get in there and if you're wearing shorts it burns your legs. Okay, because you got this dark colored interior. Whereas if you have a light colored interior, typically it's not nearly as bad. All right, so darker colors will absorb that energy and heat up quicker, okay, than similar materials of different colors. All right, so looking at this diagram here, so we've got the Earth. Obviously, a lot of the solar radiation gets reflected away before it ever reaches us, which is good because there's way too much. Okay, we don't need as much as actually strikes the Earth's atmosphere. Okay, then we've got some coming in, and some of it obviously gets absorbed by the Earth, and some of it gets absorbed by water vapor and gases within the Earth's atmosphere. Some of it that hits the Earth reflects off. Okay, and when it reflects off, its wavelength gets changed slightly, and it becomes long wave or infrared heat, okay, radiation that heads back out into space. Some of that obviously gets absorbed by clouds, and some of it gets reflected back down, okay, by the greenhouse gases and things like that. And obviously that's important. We want some of that to happen. All right. So looking at this here, this diagram on this side here is talking about albedo. Okay, so we've got sunlight coming in. On a dark surface, we've got 70%, or let's just say a surface with no snow, 70% absorption, 10% okay, reflection, okay, 20% reflected off of ground areas, 10% reflected off of the water. Okay, in the wintertime, 85 to 90% of the solar radiation is reflected. All right, it's more than a complete reversal. In the summertime, 70% is being absorbed. In the wintertime, 85 to 90 is being reflected away. Okay, that leaves 10 to 15% being absorbed. All right, takes a long time to get rid of that snow. Now, What are some things that help us to melt snow? What are some things we do? Salt will help because it lowers the melting point, but salt is also white. What else do we throw on the road? Sand. Okay? Sand serves a dual purpose. It helps us to gain traction, okay? But it's also dark. And when the sun comes out, it lowers the albedo of the snow that's on the road, and thus the snow will heat up quicker and melt faster. All right? So we throw sand and salt on the road for two reasons: traction, and it helps to more quickly melt the snow. So if you were wanting to get the snow in your yard melted, take some of the sand and, well, don't take too much of the salt, but take some of the sand off the road, throw it in your yard. Okay? Make that snow a little bit darker, all right, and it'll melt a little bit quicker. Yeah? All right, so atmosphere here. Gases present in the atmosphere help maintain the Earth's temperature. We already talked about this a little bit. Greenhouse stuff like CO2, okay, CFCs, chlorinated fluorocarbons, okay. Methane, where does that come from? Cow farts, yes. Okay, it's true. That's where it comes from. Okay, also from types of bacteria called methanogens. Okay, and things like that that can produce methane. You and I produce methane. Anything that eats other material for food does produce some methane. All right, and that stuff does collect. Okay, ozone and nitrous oxide. Okay, allow incoming radiation through, but then prevent it from escaping back into space, acting as a greenhouse effect. All right, so this diagram here on the top is sort of showing that. Okay, you got the light coming in, some of it's absorbed, some of it's reflected, some of it gets back out, okay, but a lot of it gets reflected back down, okay, to the Earth, okay, and hits us a second time as heat waves and infrared radiation, which is important for maintaining temperature. All right, sorry, and this picture here I threw in just because I found it the other day. This diagram is showing like around Mount Robson, which is a tall peak, okay? And you can have clouds just appear at the top of it, okay, because it's so high. So if you've got a moist air mass moving along and it moves along towards the mountain, you don't notice that there's moisture in the air. There's no evidence of it. But as it gets pushed up and over, that moisture does what? It cools and condenses, okay, and then it appears as a cloud. You get a little bit of snowfall on the top of the mountain, and this cloud goes over the top, and you can see that as it goes over the top and starts to descend, it starts to get thinner and it disappears again. Okay, that's that rain shadow effect we talked about before, but I didn't have a real picture of it. That's a real picture of it. Okay, that's the rain shadow effect. All right, hydrosphere. Hydrosphere is talking about all the water, and there's lots of it, okay, on the surface of the Earth. Okay. And water plays, like we said, an important part in transferring energy because it touches a lot of places on Earth. It has a high heat capacity, which we'll talk about later. Okay, is the hydrosphere. So that can be water vapor, liquid, water, ice. Okay, less than 0.1% of all the water evaporated from the surface of the Earth actually falls back to that spot. All right, so don't get the idea that, oh, well, if the water evaporates, it's okay, it just comes right back. Well, it comes back to the Earth, but it doesn't come back to you. Okay, the water cycle will cycle all that water. 100% of it stays in the Earth's system, but there's no guarantee it comes back to you. All right, if that was the case, we wouldn't have any deserts. All right, because any water evaporated from them would fall right back down. But that's not the case. In fact, for us, most of the water we get doesn't actually come from here. It comes from where? Yeah, British Columbia. It comes over the mountains, okay? It's evaporated off the oceans and things like that and moves towards us, okay? And then falls here. It's not that it's evaporated here. It comes from other places. Wind brings it in, okay? Things like that. All right. So the water cycle does transport that water around, and that can lead to a lot of energy transfers. The biggest energy transfer is something we call latent heat. Okay? Latent heat works like this. At the equator, some water is evaporated from the ocean, let's say. Okay? Does it take energy to do that? It does. All right. That water vapor now moves northward. Let's say it's coming straight for us. Okay? As it gets to us, it starts to cool. All right? And when it cools, it condenses, turns back into a liquid. When it does that, the energy that it absorbed in turning into a gas is released. All right, so it's essentially like you stored up a whole bunch of energy and moved it to another place, and then when the water condenses, that energy gets released to the new area and actually warms it up. All right, so latent heat. is energy that is moved through water changing state or moving through the water cycle from one place to another. All right. Same thing happens when water freezes into ice. Energy is released in that process into the surroundings. That's why the water itself gets colder and changes state. Okay, everyone follow me there? So latent heat is this energy that travels with water vapor from one place to another. All right, so the water cycle. How many times have you been beaten over the head with this in your academic career? Lots, like practically every year. One more time. Okay. All right. So you got the water cycle here. We got energy coming in. We got evaporation. Okay. Over here, evaporation turns that stuff into water vapor. Okay. We also have this process, evapotranspiration, which means it's water that is turned into a vapor as the result of photosynthesis. Okay. So that might be a new one. I don't know if you've had that one before. Okay. That's as a result of photosynthesis. Okay. The end result is the same either way. Water vapor is now in the Earth's atmosphere, and it has energy associated with it. All right. That water vapor begins to cool, and it can fall in various forms of precipitation, as snow, as hail, as rain, doesn't matter. Okay. It falls down back to the Earth's surface. When it gets to the Earth's surface, okay, now it's probably going to either be absorbed or it's going to run off. Now, we don't call it absorption. We have to have a more difficult name to remember because it's science and we have to feel important. Okay? The absorption of water is called infiltration. Okay? It's water that's essentially percolating down through the soil, okay, and into deeper levels of the ground. All right? If you've ever made coffee, it's kind of like that. Water kind of moves between the grounds, okay, in the coffee filter. Well, that's how water moves through the Earth's soil, okay? It just percolates and moves between the soil particles, all right, and then is slowly absorbed, all right? This is an important process, not only because it means that the soil gets moisture, but it also helps to replenish underground water sources. Okay, we tap those with wells. All right, most of Okotoks's water supply is actually from wells. Okay, the river recharges them. Okay, but we draw from the wells. All right, and so infiltration recharges aquifers, and aquifers are what we tap with a well. Everybody follow me on that one? Okay, so to have infiltration, though, you generally have to have water sitting there on the surface someplace. Okay, if it's just running across, most of it will just continue to run and not be absorbed. All right, you've probably seen that, right? Like, you know, when water gets, you know, kind of cuts a channel, the water just runs effectively through that channel. It doesn't absorb very much. Okay, we need it to sit there. So we need places like wetlands, okay, sloughs and things like that. Those are places where the water can sit and slowly infiltrate. All right, those are, so when we destroy wetlands, we're actually inhibiting the ability of water to recharge our water supplies. Okay, so something to think about. All right, so you got infiltration and you've got runoff. Okay, runoff is always gravity driven, so it's always going downhill and towards what? Yeah, the lowest points on the Earth's surface, the oceans, lakes, things like that. Okay, places where it can catch. All right, and then once it gets in there, then the cycle can start again. All right, most of the Earth's water, okay, we're talking 97% being most, is salt water. All right, less than 3% is fresh, okay, and this is the stuff we want, fresh water, because it's drinkable, okay, usable for cooking and things like that. Okay, 3/4 of all fresh water, unfortunately, is found in a solid form. Okay, so 3/4 of that 3% is frozen. Okay, either on glaciers in our mountains or in the ice caps of Antarctica and the North Pole, okay, places like that. Okay, the other nearly 1/4 is groundwater and is found in underground water-bearing porous rock. So actually very little fresh water is actually in lakes and rivers. Okay, when we're talking about the actual percentages, and that's because rivers are always moving. Okay, and well, lakes aren't, but lakes are generally pretty small, with the exception of, you know, like the Great Lakes and things like that. All right. Okay, and this diagram here is just kind of showing you the well process. Okay, so you got here a well that is going down into an aquifer. Okay, an aquifer is an underground saturated zone. Okay, where water can be found. It's not an underground lake. Sometimes people get in their minds these pictures of underground caverns filled with water. Okay, an aquifer isn't like that at all. An aquifer would be like if you took like pea gravel, the stuff you'd put in an aquarium, and filled a glass with it, and then poured water in. Okay, and the water would fill the spaces between the gravel. Okay, that's what an aquifer is like. All right, it's porous rock that has water within the pores. Okay. All right, so we've got obviously oceans being our main store of water, but not fresh. Okay, we've got rivers, waterfalls, etc. that have some fresh water. Biggest store of fresh water, okay, glaciers. All right. Are we fortunate here in Canada that we have lots of those? Yes. Are they getting smaller? Yes. Okay, that store of water may not always be there, okay, because the glaciers are shrinking and they are shrinking quite rapidly. Okay, that is the Robson Glacier right there. Okay, when I was there, and well, you can see that was 2003, so it was a long time ago. We were hiking up to it. We passed this sign that said, in 1901, the Alpine Club of Canada marked this point as the toe of the Robson Glacier. It was a sign. There was no glacier anywhere. Okay, we couldn't even see the glacier yet. All right, so in 103 years, okay, it had receded to the point where we couldn't see it. So we kept walking, and about 1.5 kilometers later, we got to the toe of the glacier. Okay, now that's not just this is not just a two-dimensional thing. Okay, not only did it get shorter, but this glacier, you can see the valley walls here, used to fill this valley as well. Okay, so we're talking a lot of melting and a lot of decrease in the size of these glaciers, and that's just in the last 100 years. All right, so 1.5 kilometers shorter and probably 0.5 kilometer thick gone. Okay, you go back 20,000 years and where we stand right now would have been under a 1 kilometer thick sheet of ice. Okay, that was the Laurentide ice sheet. It covered almost all of North America, kilometer thick. Okay, it was a big deal. It's receded quite a bit, obviously, in the last 20,000 years. Okay. All right, and last part of the Earth that we got to talk about here is the lithosphere. Okay, the lithosphere is the solid or rock-containing part. Okay, because litho means stone. Okay, so the lithosphere is the part of the Earth that is made of rock. Okay, so all rock on the Earth, no matter how small, is part of the lithosphere, and the most important part of the lithosphere is the soil. Okay, so that is essentially the topmost layer of the crust of the Earth. Okay, so to a geologist, is there such a thing as sand? No, to a geologist, a beach is made of countless number of tiny little rocks. Okay, that's true. Because where do you get sand from? The weathering and breakdown of rocks. Okay, so it really is just countless pieces, little pieces of rock. Okay, and so anytime we're talking about any part of that rocky part of the Earth, we're talking about the lithosphere. The lithosphere is important for absorbing solar energy. All right, it obviously has different colors and things like that, but it doesn't move. It's not fluid. Okay, it doesn't transfer energy very well from place to place, but it's great at absorbing it. Okay, its temperature can increase quite rapidly when exposed to sunlight. Okay, when the sunlight goes away, can it decrease quite rapidly? Yes. Okay, the Earth, the crust or stone part of the Earth doesn't retain heat all that well. Okay, the ocean does, but the stone part of the Earth doesn't. Okay, so it's important in that it can absorb the energy and then heat the things around it, like the atmosphere. Okay, and help to heat that up a bit. Okay, soil, like we said, topmost layer of the Earth's surface, layer in which plants will grow. Okay, and it is an ecosystem all its own. Okay, it has both biotic and abiotic parts to it. Okay, biotic parts are the living things. Abiotic things are the non-living things. Okay, so abiotic things would be inorganic chemicals, air, water, decaying material. The biotic parts would be the living organisms. All right, now looking in this picture here, is this soil here? Yeah, it looks like rocks, but it's soil. Okay, not all soil is necessarily good. All right, that soil would not certainly be considered very fertile. Something can grow in it. That mesquite bush is doing just fine there. All right, but were you to plant a palm tree there, it probably wouldn't fare very well. All right, but anything that can act as a reservoir of water and nutrients is a soil. All right. Okay, structure of soil. Just so we're understanding here, soil is made of layers. You probably know that if you ever dug a hole as a kid. Okay, you had like the topsoil, and then you had this kind of clayish like stuff, and then you started hitting more and more rocks. And if you go deep enough, you'll eventually hit the bedrock. Okay, which we call parent material. Why do you suppose we call the bedrock parent material? What comes from it, Julia? The soil on top. Okay, the soil on top comes from the weathering of the bedrock. All right, so whatever rock you have in an area determines what kind of soil you have there. All right, around here, our soil is kind of a light brown, and it's very gritty because our bedrock is made of what? Nobody knows. Okay. The bedrock around here is sandstone. Okay, most of the bedrock around here is sandstone because, okay, this area several million years ago, several hundred million years ago, was actually covered by a sea, an inland sea. Okay, and so lots of deposits from rivers and things collected here and were cemented together to form sandstone. Right, so around here we typically have sandy, grittier, light-colored soils. If you go further north, where there's more limestone, you typically get finer, darker-colored soils. Okay, and so on and so on. If you go to a place like Prince Edward Island, okay, they have very red dirt there because the rock they have there is very high in clay, okay, and it makes kind of a red looking rock. Okay, it makes red looking soil. Everyone follow me on that? Okay, so the type of rock you have in an area determines the type of soil. So looking at the layers here, you can see the grass up here on the top, so this would be our layer of topsoil. Right, and then below that, okay, you've got this kind of clayish layer, and then below here, this is just rock, okay, in this area. So this is the A horizon, the B horizon, and the C horizon, okay. So sometimes the diagram will show organic materials, okay. That's part of the A horizon, okay. The B horizon is the subsoil, it's mostly clay, okay, and then down below, weathered, decomposed rock, and solid rock, okay. We don't typically consider this to be any different than the C horizon. Why is the clay always below the dirt? Anybody know? It ends up being heavier because it gets compacted by the stuff on top. Okay, but it's actually because clay is very fine. If you've ever felt dried clay between your fingers, it feels like flour. Right? Very, very fine. Whereas sand and things like that are much grittier. Okay, so they're much more coarse. So the fine stuff can actually move with the water in between the larger particles, and so it collects underneath. Okay, I mean, when you played in the sandbox as a kid, right, and you dug through, there was always clay on the bottom, right? Clay underneath. It's not because your parents put clay at the bottom. Okay, no one puts clay at the bottom of a sandbox on purpose. It's just gets there as a result. Dust collects and falls on your sandbox, and then water washes it down through the sand. Everything moves through the sand because sand is big. Okay, the particles are big, and other particles are much finer, and they can move through it and collect underneath. Okay, and so you get this sealing off layer of clay below. Okay, that stuff, clay, is rotten for growing anything in. All right, clay holds onto moisture so tough, okay, that plants can't extract it out. All right, and so they really have a hard time growing in clay. They'll actually grow better in sand than in clay. All right. Okay, so like we said here, soil structure, A horizon is the topsoil, so it's typically dark. Typically, there are some exceptions to that. Okay, and it contains decomposed rock, living organisms, decaying organic materials, so dead plants and animals and whatever else. Depending on the area you're in, the A horizon can be very thick or practically absent. All right, what kind of places do you suppose have the thickest topsoil or A horizon? That's what everybody says. Whenever I ask that question, people think, oh yeah, the rainforest, because it's got all these big plants. Believe it or not, the rainforest has practically no topsoil because it gets washed away all the time. It's the most easily weathered and eroded part, all right? And so because it's always flooded, that part's always going away. The plants actually pull nutrients right out of the flood water and grow out of the clay. They put their roots down in the clay and then absorb their nutrients from the water that sits on top of it, all right? The biggest, thickest A horizons are on the prairies, because every year the grass dies and decomposes and new blades grow up from underneath. Okay, another place that can have thick A horizon would be like a deciduous forest, a place that loses its leaves every year and always builds up this layer of organic material. Okay, so any places that will build up organic material and allow it to stay there will build up thick A horizons. The rainforest, that doesn't happen. Anything that falls to the ground is either rapidly decomposed or washed away. Okay. So typically, okay, the prairies will have very thick ones. The mountains will have very thin ones. Okay? In fact, they'll have almost no A or B horizon, because what's right at the surface? The rock. Okay? There hasn't been enough time to build up very much soil. So typically, the closer to the surface the C horizon or the parent material is, the younger that soil is. All right? So the thicker the soil is, the older it is. The thinner it is, the younger it is. Okay. All right. So B horizon. Okay. Little or no organic material. Rock is less decomposed, so you may find chunks of rock. Okay, in the B horizon, and lots of clay for the reason we talked about before. It's fine and it can move down in between the larger particles of the topsoil. Okay. So typically it's light brown to red. Okay, in color. All right. This is like a Prince Edward Island type of soil, high in red clay. Okay. Anyone ever been to PEI? You can buy the dirt shirts there. They take like white T-shirts and they put them in the muck, and they turn red. Well, reddish brown. It's their big tourist trap thing. You buy a PEI dirt shirt, okay, dyed with PEI dirt clay, whatever. Yeah. Okay. All right. Tropical rainforest, like we were saying here before. Okay. Practically no A horizon. It's very, very thin, but a thick B horizon because clay will cement itself together and not erode. Right? Whereas the lighter, more coarse materials of the topsoil are easily moved away. All right, and then lastly, your C horizon is your parent material, your rock. It's the stuff your soil came from. Okay, this is a typical prairie soil horizon, or sorry, soil profile. So you got your A horizon kind of in here, all right, and then you've got your B horizon kind of in this area here where you're starting to get chunks of rock. Okay, and then you got your parent materials to your bedrock. Okay, near the bottom. Everybody with me on that one? Okay, if you were to dig a hole around here, okay, so you know, if someone gets their basement dug next to you, they're building a new house, go and have a look. All right, because that's what you'll see. All right. Okay, solar energy budgets. What happens with solar energy when it comes to the Earth? Okay, so the Earth is a system. What kind? We talked about 3 in the last unit. Anyone remember? Open, closed, and isolated. The Earth would be open. Okay, the Earth is an open system. All right, energy comes in very easily from the sun, but it also can bleed away into space. Okay, anything that gets out of the Earth's atmosphere goes back into space, and we lose it. So it's an open system. Okay. So we got this input of energy. Some of it gets reflected, okay, and re-radiated. We call that, okay, re-radiated energy. Okay, that's an output. Okay, we're losing that energy. All right. We can draw a simple model of the globe like this. We have solar input and reflection and emission from the Earth. Okay, so a lot of it gets reflected away. Some of it gets absorbed, just enough for us to maintain sort of, you know, life on Earth and constant temperature and things like that. Okay, so looking at this diagram here, it's probably a little bit more useful here. Okay, so incoming solar radiation at the top of the atmosphere is 7 million calories per square meter per day. Is that a lot? Yeah. To survive, you need to have about 1,500 to 2,000 calories a day. Okay, this is 7 million per square meter per day. All right, you would get fried if you were up there. Okay, that's why you have to wear a spacesuit. Right? Talk about the worst sunburn in your life. Okay, so you got light coming in here like this. Okay, as we go down, we see that more and more light is getting kind of reflected away. So we got some absorption here. So starting up here in space, we have 100% of the light coming in. 16%, okay, gets absorbed by water vapor, dust, carbon dioxide. Okay, 3% gets absorbed by clouds, right? And 51%, okay, by water and land, okay, striking the Earth. Okay, the rest of it is reflected away. So it's about half and half. Okay. All right, so we got 6% reflected back by air, okay, or scattered, okay. Some of it 20% reflected by clouds, okay, and 4% reflected, okay, by the land surface and water. Again, that's dependent on what word? How much gets reflected off the land is affected by albedo, okay. Remember, that's what determines that. Now, scattered, what do we mean by that? What's happening to light that gets scattered? It's not so much it's reflected, okay, it's not the same thing. What's light that's scattering doing? Yeah, exactly. Okay, remember the Earth's atmosphere is made up of atoms, right? Gases, atoms. Well, when it's not a uniform surface, so when light comes in and reflects, some of it reflects straight back, some of it reflects down, gets deflected, whatever, it gets scattered, okay? Kind of shot everywhere. And that's why the sky is blue. How many of you were told it's because it reflects off the ocean? That's wrong. Okay? The Earth's sky is blue, okay, because the Earth's atmosphere scatters blue wavelengths of light. All right? That's part of the reason why ultraviolet waves also get reflected and removed from the radiation spectrum before they reach the Earth's surface. Okay? Our atmosphere's composition scatters blue wavelengths of light. And when they scatter, they go everywhere. And so when we look up at the sky, it looks blue. Until the sun begins to set or rise. Okay? Then what color is the sky? More reddish orange, okay? Reason for that? When the sun is low on the horizon, it's also now having to send its light through not just the gases of the atmosphere, but the things that might be closer to the Earth's surface. Dust, smoke, okay, things like that, that scatter light differently. They scatter the longer wavelengths of light like red and orange. And so as it sets, the sky appears more orange because it gets scattered differently. Okay? And that's why at night, it's black. Okay, there's nothing to scatter then. Yes. Okay, does that make sense? So it was all a lie. Okay, it's not blue because it reflects off the ocean. Because what color is the ocean? Clear. Water's clear. I don't know what the ocean looks blue because it reflects the sky. It's the other way around. See? Okay, you were told that it's the sky reflecting. No, it's not. It's okay. The sky reflects off the ocean. That's why the ocean looks blue. Okay, all right. Okay, solar energy budgets. Without a doubt, obviously, the biggest input into our global system is the sun. Okay, we are talking like 99 point infinitely 9 percent of all the energy available on Earth is from the sun. Okay, very, very small amounts are produced by gravity, magnetism, and geological forces like volcanoes, okay, and things like that, and the heat of the Earth's core and all of that. Okay, doesn't really contribute to the energy used by living organisms on Earth. All right, I mean, how many living organisms use energy from volcanoes? Like, yeah, practically none, really. Okay, a volcano's kind of bad for living things. A little hot, right? Okay, there are a few deep sea communities of organisms that are around hydrothermal vents, okay, and they can use sort of geothermal heat a little bit, okay, but very, very few. Almost everything relies on the sun, okay, as a source of initial energy. All right. Now, what about us as human beings? Do we use gravity, magnetism, and geological forces for energy? A little bit. Okay, I mean, we have good technology. We use gravity a little bit because we use, in some places, tidal power, right? Which is a lot like wind power. They put turbines, okay, in the areas where the ocean moves in and out a lot, okay, and that's because of gravity. So yeah, we can harness that a little bit, okay. Magnetism, yeah, there's not too many things that actually use magnetism to generate or make power, okay. Geological forces, yeah, we have some places that use geothermal energy. Iceland is a place that is primarily running on geothermal energy. Okay, but again, not a lot. All right, even your car. Okay, your car is solar powered. I'm not lying. I'm not telling the whole truth, but I'm also not lying. Okay, your car is solar powered because what does it run on? Gasoline. Where did the gasoline come from? Dead plant material mostly. Some animal, but mostly plant. Okay, it's fossil fuels, right? Coal comes from plant material. Gasoline comes from plant material. All of that. Those things all used the sun to make energy. And when they died, okay, they got buried and transformed, and the energy that they had converted into sugars during their lifetime was converted into other forms, like coal, fuel, oil, things like that. So the energy that you burn in your car now was solar energy 500 million years ago. So technically, your car is solar powered because the energy you're burning in it came from the sun at some point. Okay? The only problem is that those plants took a lot of useful carbon dioxide out of the atmosphere while they were doing all that, and now you're putting it back in. Okay? It is a cycle. All right? They took it out and hid it for millions and millions of years, but we're putting it back in. All right? So it's solar powered. So next time, like a real environmentalist really gets in your face, you can tell them you should drive a solar powered car. And they'll probably leave you alone. It's sort of true. Okay. All right. Well, sometimes people get uppity, Sometimes they get uppity, You got to use cleaner fuels. And so what do? We build the wind farm in Pincher Creek. And they still complain because it kills birds. Hey, you just can't win, right? Oh, but then they would say that your solar panels are blocking light from hitting plants on the Earth's surface. So there's no pleasing them. No pleasing. All right. Atmosphere. I'm just being facetious here, guys. Obviously, you know that, right? Okay. Atmospheric transfers. Okay. Like we said, the biggest place where energy is transferred, okay, on Earth is within the atmosphere because it's the most fluid and it's in contact with everything. Okay. And it uses this form of heat transfer, convection. Okay? Convection is the movement of fluids, okay, as a result of differences in temperature. So hot air rises, cool air descends. That is the simplest example of convection. All right, we use it in our homes all the time. Okay, on the main floor of your house, where does the hot air come out? Where are the vents that the hot air comes out of from your furnace? On the floor. No, that's cold. That might be a cold air return. No, I don't mean where the gases get out. Okay, where the warm air comes out. Those are on the floor, right? Okay, so they're on the floor for one reason. That's where the coldest air is. Okay, we want them to be there because hot air is coming out of them, and the hot air is going to rise, and it's going to come into contact with that cold air. Okay, and it's going to create a convection current that will more effectively transfer the heat within your home. Okay, in your basement, if you have one like mine, the vents are on the ceiling. Doesn't work nearly as well. All right, because you've got hot air already near the ceiling, and hot air is coming out of the vents near the ceiling, and you don't get as good a flow of energy in your basement unless you have underfloor or in-floor heating, and then you do get very effective, okay, convection in your basement. All right, so we want to use things like that. Julia. Differences in temperature. Yeah. Okay, so this is a convection current right here. We're showing one of these old school like hot water radiator things. Okay, so you've got hot water in here, and that's transferring energy to the surroundings. Hot air is rising, cool air is descending and coming in here. It gets heated, okay, moves around. Do we help that a little bit in our homes? Yeah, your furnace has a big fan, okay? Because we want to increase the amount of convection that happens by forcing the air to move. All right? If you just had a bunch of heat elements on the floor, okay, it wouldn't be nearly as effective. It would work, but having the air move and be forced to move also helps. It increases that convective transfer of energy, right? On the Earth's surface, this happens naturally. We don't have big fans, okay? This just happens. Light strikes the Earth's surface, the air near the surface heats up, and it rises, and cool air moves in to replace it, okay? And that starts that convection current going. All right? Everybody with me so far? Okay, so convection is like our #1 form of energy transfer on Earth. Okay, we sometimes call it wind. Okay, because that's what starts wind. Okay, if you've ever been to the ocean, okay, in the morning, it always feels like there's this kind of cool breeze coming in off the ocean. It's called a sea breeze. Okay, the reason for that is that near the Earth, near the ocean, the land heats up faster than the water. So you've got your land here and you've got your water here. Okay? The hot air rises above the land and the cool air moves in off the ocean to replace it and causes a convection current to happen. Okay? Simple example of it. All right? Okay. So that's what happens in fluids. Liquids and gases can allow convection to occur, but convection doesn't happen in a solid. Why not? They don't flow, right? Their particles are too closely packed. Their particles can't switch places. Okay? So in a solid, because the particles can't switch places, you can't get this current to set up. All right? So instead, you get what's called conduction happening. So if I've got this solid material here and I heat up one end of it, the individual particles start moving around. The hotter they get, the faster they move. But they can't move very far. They can only move far enough until they hit the next one in line. Okay? But when they hit it, do they transfer energy to it? And so on. So you get this kind of domino effect of heat transfer, okay, towards the other end of a solid material. But it isn't very fast. Okay? It's part of the reason why you use a wooden spoon to stir something in a pot that's very hot. Because if you use a metal spoon, eventually the handle of the metal spoon will get too hot for you to hold on to, because eventually the conduction will transfer the heat up the spoon. It is a slow process. It's not something that would work on a large scale like on the Earth. Okay? All right, so this is again showing you that convection thing here. Okay, you've got hot stuff moving up, cool stuff moving in, okay, to replace it, so you get this flow. Okay, yeah. So convection is super important, probably the most important one. Okay, sorry, so we got, this here was conduction. I don't have that on, sorry, conduction. Okay, so conduction, okay, happens in solid materials, but for either one of these to happen, we need the third form of energy transfer, and that is radiation. Okay, radiation is heat transfer through waves, okay, and that's essentially what our solar energy is. Okay, solar energy gets here through radiation. Okay, not all radiation is bad. Okay. Right now, you are being bombarded by radiation. Okay, you're not turning into a mutant. You wouldn't do that anyway. Okay, but you're getting hit by radiation all the time. It's just not harmful stuff. Okay, the stuff that comes from our lights is radiation. It's visible light radiation, but it's radiation nonetheless. Okay, you are radiating away from yourself right now. Okay, heat is a form of radiation. Okay, you are radiating heat away from your body right now. You are a source of radiation. All right, but radiation gets this bad rap because people always assume that it means, you know, the glowing green goo that comes out of, you know, a nuclear power plant, which actually also isn't true. It's not glowing or green, for that matter. Okay, but it's radioactive. Okay, and that stuff is, that's different types of radiation. Those are very harmful. Okay, but not all forms are. All right, so water condensing in the atmosphere. This is latent heat, and I was talking about that earlier. Okay, latent heat, second to convection in terms of the amount of energy it transfers on Earth. Okay, second to convection. So water condensing within the atmosphere releases the latent heat and warms the surrounding atmosphere. All right, so if we have, like we said, water vapor that evaporated off of the ocean near the equator, okay, it contains potential thermal energy or latent heat. Okay, that stuff moves more northward, and begins to cool. As it cools, it reaches the temperature where water turns back into a liquid. When it does that, it releases the potential thermal energy as heat, all right, and transfers that to the new area. All right, so energy can be brought from the equator to more northerly parts of the world in moist air masses, okay, as latent heat. All right, so there's convection. That's just hot air rises, cool air descends, and we'll look at how that works when we look at global wind patterns tomorrow. Okay, and this latent heat. Okay, those are the two really big ones. Okay, now heat energy taken from the environment here, heat energy released into the environment. So what we're looking at is the three states of water here. So we've got ice. Okay, obviously to melt ice, do we have to put heat in? Yes. Okay, so if I'm melting ice, I have to put heat in, I get liquid water. Okay, if I want to evaporate liquid water, I got to put more heat in, and then I'll get vapor. Okay, if I cool that, I'll get condensation. That means energy has to be released. If I had to put energy in to get this, when I give it back, the energy has to come back. All right, law of conservation of energy. All right, when water freezes into ice, okay, again, that heat gets released, and then there's these two processes that are exceptionally rare. Okay, sublimation and deposition. Very rarely does water skip a state. Okay, very rarely does water ever go directly from ice to vapor, because it takes a ridiculous amount of energy or a ridiculously large lack of pressure. Okay, on Mars it can happen. Okay, where there's practically no pressure, ice can essentially turn straight into vapor. Yes, dry ice. Carbon dioxide does that, yes, very easily. Okay, in fact, you almost never see carbon dioxide in a liquid form. All right. Okay, so lithospheric transfers. Like we said, not a lot of energy gets transferred from place to place in the Earth's crust. Okay, but the Earth's crust plays an important role in absorbing energy. Okay, when it absorbs energy, then it can slowly allow that to transfer or reflect back into the atmosphere, okay, and warm the atmosphere up. So that's really its only role, okay, is to do that. The other role that the lithosphere takes in terms of energy transfers is that it allows this to happen. Okay, without the lithosphere, there'd be no soil. With no soil, there'd be no plants. Okay, no plants, no photosynthesis. So it doesn't really transfer so much of the heat energy as it helps to form and transfer the chemical part. Okay, so we said three things could happen to energy when it struck the Earth's surface. It could be absorbed. Okay, it could be reflected. Or used, okay, / converted. Okay, and the lithosphere is most involved with the third step. Okay, questions on any of that? So there's not a lot of recall stuff in this. Okay, this lesson is going to be tested mostly with real-world application type questions. So I would ask, if you were going to build something that had to do this, what kind of things would you need to consider? Well, if you wanted it to transfer energy or hold energy in, I would want to use, things that would reflect the energy back and stuff like that. Okay, so this is going to be more of an application type lesson as opposed to I'm going to ask you recall questions about the atmosphere and the lithosphere and whatever. Okay. All right. That's it. You've got about 10 minutes to talk to your group about your climatograms. Okay?